Hello everyone, and welcome back to the Fluctus Channel. The U-2 spy plane is a high-altitude reconnaissance aircraft developed during the Cold War to gather strategic intelligence. Flying above 70,000 feet, it could observe hostile territory beyond the reach of most air defenses. Long, slender wings allow efficient flight in thin air, but demand extreme precision from pilots. The aircraft carries advanced cameras, sensors, and signals intelligence equipment. U-2 missions have monitored missile tests, troop movements, and nuclear programs for decades. Despite satellites and drones, the platform remains valuable, offering flexible tasking, rapid deployment, and real-time intelligence collection for national decision-makers worldwide today. Despite the overstated design features built into aircraft carriers, things become intriguing when a larger aircraft arrives for operations. The U-2 Dragon Lady, a truly unique reconnaissance aircraft, was never originally intended to operate from an aircraft carrier during its initial design phase. The downing of a U-2 by a surface-to-air missile over the Soviet Union in 1960 raised concerns about the CIA's reliance on high-altitude reconnaissance using the Dragon Lady. Consequently, the CIA, together with the U.S. Air Force, made a strategic decision to make the U-2 carrier capable. While landing a U-2 on a runway typically requires a chase car operated by a qualified pilot and a coordinated team of airmen, the CIA made history by successfully landing a U-2 on a flight deck. To make the Dragon Lady carrier capable, Lockheed reinforced its landing gears to endure the extreme forces of catapult launches and arresting hook engagements. Furthermore, the aircraft was upgraded with an arresting hook and a pair of spoilers on each wing to enable carrier landings. The carrier-capable variant was designated U-2G and achieved its first landing in March 1964. The bicycle-style landing gear and the 105-foot wingspan make the launch process particularly challenging. Unlike a conventional fighter pilot, a U-2 pilot carries the added burden of wearing a heavy pressure suit. The aircraft features mid-span outrigger wheels, known as pogos, which maintain lateral balance during taxi and takeoff. Once aligned on the runway, the pilot increases throttle to begin the takeoff roll. After becoming airborne, the pogos detach from their wing-mounted sockets. The mobile chase car serves as a wingman, guiding the pilot from behind. The Coke bottle-shaped fuselage minimizes drag and reduces weight, supporting prolonged high-altitude flight. To maximize reconnaissance effectiveness, the U-2 can reach altitudes of up to 70,000 feet. Although the aircraft can climb to 60,000 feet in just 45 minutes, ascent rates vary depending on mission requirements. As a standard, U-2 mission can extend for long durations, sometimes exceeding 12 hours at high altitudes. Pilots wear pressure suits to withstand extreme temperatures and pressure conditions. The cockpit pressure altitude at 70,000 feet is regulated to approximately 28,500 feet, necessitating the constant use of the pressure suit. A dual redundant oxygen system ensures a continuous 100% oxygen supply throughout the mission. Bringing the Dragon Lady back down safely is the most demanding stage of flight. Due to its bicycle landing gear configuration, the pilot must keep the wings level until the aircraft sheds most of its speed. Skid plates are installed on both wingtips as the aircraft tends to tip to one side after coming to a complete stop. The Pogo team then reinstalls the outrigger wheels, allowing the aircraft to taxi off the runway. Later on, an enhanced version of the U-2 was acquired by NASA in the 80s, named the ER-2 High Altitude Airborne Science Aircraft. Both aircraft have participated in the Airborne Science Program, which focuses on collecting data on Earth's resources. Performing celestial observations, studying atmospheric chemistry and dynamics, and analyzing oceanic processes. These studies are made possible by advanced onboard instruments, including an infrared imaging spectrometer that utilizes more than 224 sensors. Operating as a flying laboratory, the ER-2 continuously gathers essential data across a broad spectrum of atmospheric sciences. One notable example includes research on severe thunderstorms in Earth's atmosphere, which was the primary goal of the dynamics and chemistry of the Summer Stratosphere Project. This initiative aimed to understand how powerful storms impact atmospheric chemistry, particularly regarding the ozone layer and climate change. To reach altitudes of up to 70,000 feet, the aircraft's capabilities made it ideal for flying above thunderstorm overshooting tops and collecting data on water vapor, ozone, aerosols, and trace gases. Although the aircraft is primarily used to study atmospheric conditions and phenomena, its advanced instruments also enable the detection and monitoring of forest fires. This aircraft is equipped with an virus spectral instrument developed by a jet propulsion laboratory. Combined with its ability to sustain high-altitude flight for extended periods, this allows teams to gain a wider situational overview. This technology enables real-time mapping of affected areas, providing emergency response teams with valuable operational data. As a result, responses become faster and more effective in addressing the most critical zones during such events.
Wait a minute, you flipped the switch.
Earth observer satellites, try and calibrate them before they go up.
Space exploration has driven the creation of new technologies that lead to innovative devices and vehicles capable of surpassing Earth's orbit. One of the major objectives in this field is developing reusable vehicles that can travel to space and return multiple times, making space missions more cost-effective and encouraging more frequent flights. This ambition led to the development of spacecraft, such as the Boeing X-37 in the early 2000s, designed to conduct space, experimentation, technology demonstrations, and long-duration orbital research. The vehicle is the first since the Space Shuttle capable of returning experiments to Earth for detailed examination and analysis. To launch the X-37 into orbit, powerful rockets like the SpaceX Falcon 9 or the Atlas V from United Launch Alliance are required. Both rockets have served as launch platforms for the X-37 during testing phases and subsequent orbital missions. Typically, the spacecraft is housed within the rocket's payload fairing, an aluminum shell with thermal protection located at the rocket's tip. Once secured, the rocket is transported to the launch pad using a crawler transporter, a heavy-duty tracked vehicle capable of carrying massive loads. At the pad, launch control systems are linked to combustion systems operated by engineers during ignition. Over years of testing and multiple launches, engineers have gained valuable insights into improving the spacecraft systems. This progress has enabled longer mission durations and more ambitious operational goals. After 7 missions conducted since 2010, the X-37 has accumulated a total of 4,010 days in orbit, typically testing experimental payloads, spacecraft durability, or deploying small satellites. However, reaching orbit is only one part of the mission, as atmospheric re-entry and landing are equally, if not more, critical due to the significant risks involved. This is why its design draws inspiration from space shuttles, incorporating a thermal protection system made of silica ceramic tiles. Along with an advanced avionics suite, the spacecraft can re-enter the atmosphere and land similarly to a conventional aircraft. The X-37 has demonstrated its value by supporting the advancement of numerous orbital experiments. With each launch, new opportunities arise to test and evaluate emerging concepts and technologies, such as the photovoltaic radio frequency antenna module. This experiment seeks to capture solar energy in space and convert it into usable power that can be transmitted back to Earth. Continued testing may lead to the development of a consistent and dependable energy source unaffected by atmospheric conditions. Cross-sector collaboration will be essential to overcoming the challenges associated with this and future experiments. Success in such experiments, particularly those involving space solar energy, could benefit multiple sectors, ranging from military and strategic applications to civilian energy infrastructure. Other promising initiatives have included research into the long-term effects of space exposure on seeds for space crop production during interplanetary missions and permanently inhabited space bases. These experiments pave the way for future advancements in the space industry and potential space colonization. As a reusable vehicle, the X-37 offers the advantage of maintaining a continuous mission schedule, requiring only periodic maintenance and repairs in the hangar upon landing. Among the most routine yet essential space missions is the deployment of satellites in orbit for various industries and objectives. One such mission supports navigation systems, with GPS being the most widely recognized. This system relies on a network of satellites, including the latest models belonging to the GPS-3 Space Vehicle 6, developed by Lockheed Martin. The advancement of this technology has been vital for the U.S. military, delivering precise navigation capabilities while also supporting civilian users with location services. Given the importance and sensitivity of satellite components, the logistics involved in transporting them to launch sites demand meticulous planning. Every step requires equal levels of accountability and precision, from the manufacturing facility to the launch pad. The transportation of the GPS-3 satellite involves coordination among several major stakeholders, including Lockheed Martin, the U.S. Air Force, and the facility responsible for processing and integrating the satellite prior to launch. From the U-2 Dragon Lady pushing the limits of high-altitude flight to reusable spaceplanes and next-generation satellites, this narrative showcases how aerospace innovation continues to evolve in response to emerging intelligence, scientific, and strategic needs. Each platform builds upon the lessons of the previous one, proving that endurance, adaptability, and precision remain the backbone of operations from the edge of the atmosphere to orbit and beyond. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.